Hello. Are you recording?
Yes, but okay, go.
Hello and welcome. So here we are, and we're again still in chapter 9, correlation and regression. So let's look at the outline. On Tuesday, we talked about correlation, and now we're going to work on linear regression. Okay. And remember, we're still omitting 9.3 and 9.4. So for linear regression, we've got two objectives. One is to find the equation of a regression line, and the other is to figure out how to predict y values using a regression equation. Now, a regression line is still a line, and we remember our equation for a line as y equals mx plus b. So recall your general equation for the general format for or of equation of a line is y equals mx plus b. Now, what does m stand for? M is the, you got it, slope, and b is the y-intercept. We're going to be using that as we go forward. Now, regression lines. Okay, so after verifying that a linear correlation between two variables is significant, I actually want to point this part out because that's really not going to apply to us. You might ask the question, how do you verify that the linear correlation between two variables is significant? How do you verify it? This is done using tests. So remember that we omitted certain portions of section 9.1. So that's what they're talking about here. So we don't really have to worry about that. What we're going to do is essentially assume that the linear correlation between our two variables is significant. So next, we determine the equation of the line that best models the data. And this is the regression line. It's also called line of best fit. Okay. And the key term, if you're trying to Google it and find more information, is linear regression. And you'll also see it as linreg. So on your calculator, it's referred to as linreg for linear regression. So it can be used to predict the value of y for a given value of x. So notice that before we would have data. In this case, we've got 1, 2, 3, 4, 5, 6 data points. So we'd have x1, x2, x3, x4, x5, and x6, and y1, y2, y3, y4, y5, y6. Right, so remember this. And we would look to see if there is a correlation, if there's a linear correlation. And the idea is we figure out the equation of the line that best models these points. So notice, um, what would R be? We could come up with a guess for R. R is definitely going to be positive because these variables appear to be positively linearly correlated. So maybe R is about, I don't know, 0.7, just a guess, right? So it's a strong, positive linear correlation. So we've got our R. Now the key thing here is that the regression line can be used to predict the value of y for a given value of x. Now, let's get more into detail with that. We might need this slide for notes later on, so I put it in here. So in order to figure out how we're going to come up with the equation, so our current goal is to understand how to create or develop the equation for the line of best fit, we'll call it regression line, when you're given data points. So you might be given data points x1, y1, x2, y2, x3, y3, so forth and so on, all the way up to xn, yn. And the first concept we need is a concept of a residual. So the residual is the difference between the observed y value and the predicted y value. So actually that's what I should have highlighted. Observed versus the predicted y value. Okay, so for a given x value, di, this is our difference, is the observed y value minus the predicted y value. So if you look back at our screen here, right, these are all observed points. Observed points, right? So for this value of x, I, we would have this value of yi, right? And it looks like perhaps this is x2 and y2. But the question is, what the observed value of yi versus the prediction. Now, according to the equation of the line, this is the predicted value. Okay? So, just like if you were to plug in x and see what value is x set to on this line, that gives you the predicted value. Now, this is the original value. The observed value is down here. Right, so here's the observed value and the predicted value. So we look at that difference, and that is our d sub I. Okay? And for each value, for each data point, we will have this difference. Okay, so the regression line, or the line of best fit, is the line for which the sum of the squares of the residuals is a minimum. So for those of you who do calculus, what we would be looking at is minimizing the function that gives us the difference between the observed and the predicted values, right? So that's our residual. So you'd be adding up the residuals and trying to minimize that. And as we know, in order to find the minimum, what would you do? This is if you're dealing with calculus. You would take the derivative, set the derivative equal to 0, okay, to find your critical points. So that's a little bit of the theory behind how we come up with the regression line. Same thing as the line of best fit. For us, this is not a calculus-based class, right? So we're not necessarily focusing too much on the theory behind it, but I wanted to just mention it. So for us, let's focus on the fact that the equation of a regression line is going to be, this is something that we know, right? We remember this from before. This is essentially y equals mx plus b. And we still have our very familiar m is the slope, right? And b is the y-intercept. Notice that here we're writing y hat because we want to make a distinction between the predicted value. We want to always be aware and kind of make a note to ourselves that this is the predicted value. So it's not necessarily the actual value, and most times it's not the actual value. It's simply the predicted value. Okay, so this is going to be the general formula for our line of best fit. Now, let's get into a little bit more. So for the equation of regression line, y hat equals mx plus b. Here's the formula for m, and here's the formula for b. Okay, m, notice this formula, if you notice, this formula looks very similar to the formula for r, which is our correlation coefficient. However, let me point out, m is not the same thing as R. What you do know is that if R is positive, M is positive, and if R is negative, M is negative, but M and R are not the same thing. Okay? And we've got this notation here. The symbol, the sigma symbol, means you're supposed to add up the numbers. And N denotes the total number of data points. Okay? Y bar and X bar are the mean, and we'll get into this in further detail in chapter 2. Mean is the same thing as the average. So mean equals average. And the same thing down here, mean, just another word for the average. Okay? And a key thing to point out here is that the regression line always passes through the point X bar, comma, Y bar. And that's something you can check out. You can check out if M X bar plus B is equal to Y bar, always. So that's a good exercise to practice with using the notation here. Okay, so just recall. So we're just going to practice. What is the mean of a data set? So suppose your data set is 0, 1, 4, 4, 6, and 2.
It's 12:15.
Sorry. Find the mean of your data set. So if we wanted to find the mean of our data set, so here's what we'd have. So like x1 is 0, x2 is 1, x3, x4, x5, x6. So since there are 6 numbers in our data set, n is equal to 6. So here's the way we'd write the formula. X bar equals the sum of x over n. And this is saying add up all of the numbers in data set and then divide by the size of the data set. So for us, this is going to be 0 plus 1 plus 4 plus 4 plus 6 plus 2. And we're going to divide it by 6. So what we would get 10, 15, 16, 17. So we get 17 over 6, which is equal to, I'm not sure. Maybe I can look it up. I don't want to do it longhand. Oh, woohoo! 2.83. 2.83 repeating. So we can just say that's approximately 2.83. Okay? And now, of course, what I would like for you to do is find the mean using your calculator. So in order to do that, if you don't already know how to do that, right now, Google find mean TI-83 or whatever is, whatever your calculator is. Okay? And then follow the instructions and make sure you know how to find the mean. You're going to enter your data set into a list first, and then you're going to navigate to your sample statistics. Okay? All right, good. So now let's look at this example here of finding the equation of a regression line. Find the equation of the regression line for the GDP and carbon dioxide emissions data. So we looked at this. This is a continuation of the example that we looked at in section 9.1. So here's x1, x2, x3. This is x4, x5, x6. So the question is, what is n? x7, x8, x9, x10. So n equals 10. Now you can do this the old-fashioned way with the calculator, so you can do it using this formula right here. You can calculate x bar, y bar, calculate m, and then get b. Right, and that's what they do here on this slide here. So in order to, the formula the formula for M, let's write down the formula for M. Oh, no, that's too long. I'm not going to write that down. In order to carry out the formula for M, or they're just doing it longhand, they've got their X values in this column right here, right? So they added up all those X values. They got 23.1. They're going to do the same thing for their Y values. Now, the next formula they need the sum of the product of XY. So, for instance, notice to get this XY, they just multiplied 1.6 by 428.2. Okay, and you get 685.12. Right, and then you do that all along the line, and this is what this symbol means, the sum of x times y. And similarly, the sum of x squared, that means what's x? If x is 1.6, then x squared is 2.56. So they calculated x squared and then added all those up, and they did the same thing for y squared. So now they figured out these key components, and they know, lastly, that n is equal to 10. So, to calculate your m, now this is our formula right here. Right, so it's n is equal to 10. Okay, so you've got the sum of x times y. So that's up here. So you plug that in, and then minus the sum of the x's times the sum of the y's. And then, divide it. Now, I'm not going to go through all those steps like I said in class. Really, these things are calculated using technology, because in real life, you've got so much data that is not practical to calculate it by hand. Also, calculating by hand leads to a lot of errors. It's very difficult for someone else to check your work, or for you to share the information that you're doing if you did it by hand. So really, technology is what is used. But this is just showing you, this example here is just showing you how to do it if you wanted to do it by hand. Okay? And then here's a picture. Now, we already had this picture from before when we needed to do our scatter plot. For the scatter plot, though, we just had the points. Remember, we just did a scatter plot of the points. What is significant now is the addition of the line. Okay? So now that we have the line, we are saying this is what we would use. We'd use this line to try to make estimates. So, for instance, we don't know what the CO2 emissions would be for, let's say here, if X is equal to 2, right? So if your GDP is $2 trillion, what would you predict to be the CO2 emissions? Now look back in the data that we're given, and 2.0 is not here. So you can ask the question, what is CO2 emission if GDP equals $2 trillion? Right? Now that answer is not on the chart, so the best you can do is estimate. Best solution is to estimate. And in order to estimate, what we're going to do is use this equation right here. So we've got this equation. So let me highlight it right here. And we're going to estimate, we're going to plug in x equals 2. So if x equals 2, then we'd have 196.152 times 2 plus 102.289. This is our prediction. Right? So this is our prediction, which is another way of saying our estimation. And what do we get when we add that up? What do we get when we add that up? So we need 196.12 times 2 plus 102.289. 152 is down at the bottom of the screen. Okay. Times 2 plus 102.289. Okay, so we got 494.9 0.593. What are the units? What are the units? You don't know the units? Okay, let's go back and look at the data. We need to figure out, there we go, millions of metric tons. So the best solution is to estimate, and our estimate is, so using ln reg, we get, what's our estimate? Let's go back. 494.593. So we could say 494.593 millions of metric tons of CO2. Okay? And so now notice 2.0, again, it's not part of our data. So this truly is just an estimate. It's a prediction because there's no concrete evidence that you'd have 494.593 millions of metric tons of CO2, right? This is an estimate, and we're using, the way we get our estimate is by using the equation of regression line. And then here, let's see here, looking on the graph here, if we go for x equals 2, that looks like it's definitely, so if this is 200, this is 600, in the middle would be 400, right? So it looks like it's somewhere close to 500. So our picture matches the calculations that we did as well. Now, please remember that the slope of the regression line, now what is the slope of the regression line? Let me put my highlighter on. Slope of the regression line, that is m, right? Because our regression line is y hat equals mx plus b. It's not the same as a correlation coefficient. And the correlation coefficient is, the standard notation for that is, what is it? R. You got it. So M is not the same as R. That's the key thing there to remember. But if M is positive, then R is positive, and if M is negative, then R is negative. Because M gives us the slope of that line of best fit. So if R is positive, that means that the scatter plot has to be somewhere where the points are kind of positively correlated, linearly correlated. So when we go to draw that line of best fit, the slope of the line of best fit will also be positive, right? And if the slope of the line of best fit is negative, that means that the points, right, your two variables must have been negatively linearly correlated. So R would be negative. So just one last word as a reminder for R tells us the strength and the direction, okay? And R is always in between 1 and -1. But M can be anything. M can be anything, right? So M can be, suppose you had some points that were like this. This M is going to be is going to be a big positive number because your line of best fit has a very large positive slope. R is going to be close to 1. So here's an example where M is really big and positive, and R is close to 1. Right, so maybe M is like 100 or M is 1,000, and R is close to 1, okay? So that's another way to remember the difference between M and R is that M can be any number, can be not anything. It couldn't be a car. M can't be a vehicle. Let me erase that. M can be any, any number, can be any number, right? Whereas R has to be a number in between -1 and 1. So R is bounded. Okay. Now, here's what we love. Here's what we're going to be doing using technology to find a regression equation. So use a technology tool to find the equation of the regression line for the Old Faithful data. So just to double check again, I like to do this and I encourage you to do it when you're using your technology. And you want to verify when you're entering in your data to make sure that you're kind of on track. One way is when you've entered in, so on your calculator, you'll have L1, L2, L3, so forth and so on. It'll look like that, right? So the very first thing is you should have the same number of points entered in, right, for L1 as you do L2. So if you've got one more point in L1, then you made a mistake somewhere. And the same thing is true for L2. That's one way is to make sure that you should both columns should have the same number of entries. Another way to check is to just count what is in and make sure that you end up having, n entries for L1 and L2. So let's just count. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so here n is equal to 25, right? And we passed out some information. I passed out some handouts that give explicit instructions on how to find the linear regression equation. And I trust you will see those. So, so you can look here and you can see LinReg, as I was telling you, for
It's
TI-84 plus.
12:30.
Thank you. LinReg. Notice LinReg gives you a printout of some very useful information. Instead of using M, LinReg uses A. Okay, so for us, A is the same thing as M. Okay, LinReg uses Y as opposed to Y hat. Your textbook and I will use Y hat. Okay, and M, R is also used. Okay, and so it gives you this added information here of R. This is, remember, R. What is R? R is your correlation coefficient. And here's a perfect example here. R is very close to 1, but your M, your slope is like 12.5, right? So remember how I was saying that M doesn't have to be in between -1 and 1, whereas R is always bounded. And so here's a perfect example. Okay, R squared is important. R squared gives you information. It gives you even more information about the fit. We won't go into R squared too much. We really won't go into that. Now, the last thing we're going to learn today is predicting Y values using regression equations. So that's the last thing we're going to work on here. Now, we got into this a little bit. And essentially what you're going to do is, if you're trying to predict Y values using your regression equation, what you're going to be doing is plugging in whatever you're trying to predict, right, for X. So here it says the regression equation for the GDP in trillions of dollars is right here. So this equation was calculated in the first example. So you've got your equation here, right? Use this equation to predict the expected carbon dioxide emissions for the following GDP, right? Now, so here, in order to do this, you just plug in X equals 1.2. So let's plug this in. So for number 1, we would get Y hat equals 196.152 times 1.2 plus 102.289. Then that is going to equal, what does that equal? I don't know what it equals. What does it equal? Maybe I can just use this. It's going to equal 196.152 times 1.2 plus 102.89 102.28, not there. If we look at our original data, the smallest number we had is a 0.9. That's the smallest number. And the largest number is a 4.9, right? And when we go and we sketch it here, that shows up. Let me show you where that shows up. 0.9. Do you see how this is the smallest number we had and the largest value of x? Right, it's right here. So predictions are good whenever x is in this range. If you try to use this equation to predict what happens when your GDP is 10.0, it's not going to be as reliable of a prediction, okay? Because these are local phenomenon, and the estimations are based on and are assuming that your x values are in or close to, right? Because or close to the range of the data, okay? So look, it says here, it would not be appropriate to use the regression line to predict carbon dioxide emissions for GDP products such as 0.2, because that's just too small, or $14.5 trillion, okay? All right, so that is that. We've done here essentially two things: found the equation of a regression line and used it to predict y values. Make sure you use technology, to find the LinReg equation, right? So make sure that you're very, very comfortable with doing that with your calculator. And also don't confuse M with R, okay? So M is the slope of your linear regression line. R is your correlation coefficient, and don't confuse them with each other. All right, that's it. Thanks. Hold on, wait, were you able to see? I don't know if you were able to see the last part here. Uh-oh. Because I think I have my calculations going. Okay. I think pretty much though. I think you can work it out. All right, bye.